So now, in order to improve this flip-flop latch, also called the set reset flip-flop, we have this circuit which is called the D-type latch or the D-type flip-flop, which has a little bit of circuitry before this we already analyzed, and this will remove that unwanted condition of the forbidden case, producing, to make a long story short, this truth table. So if we are careful and we analyze this thing step by step, we will arrive at this result. So now we have two inputs. One is called clock and the other one is called data, and then two outputs, Q and its complements, Q negated. And this thing is useful in order to build this circuit here. So we can now analyze what happens when we connect this Q bar output back to the data input, and we analyze what happens at the Q output when we have an input to the clock input. So let's analyze this situation. So now we have the input, the clock. So we can imagine we can attach a clock device as we studied before to this thing. So in order to understand the behavior, we have to read the truth table. So if the clock goes at 1 and the data is 0, then Q next is 0. So if the data is 0, once the clock arrives, Q goes at 0. It means that Q bar goes at 1. Now, after this situation, the clock goes at 0. And according to this truth table, nothing happens because we are in a hold condition. But the data has changed from 0 to 1. So now we have a 1 this time. But this 1 is not already passed at the output. It needs to be triggered by the clock. So another impulse of clock will make the data, now the data is 1, to go represented at the output. So now we have a 1 and therefore Q bar is 0. So the next value that will be triggered by the next input pulse of clock would be 0. So if we study this the way we just told a few moments ago, we can plot the value of the Q output and we realize it's like this. So it stays high for the entire cycle of clock, then it stays low for another cycle, then it goes high and it stays high for an entire cycle, and so on. So this thing is a so-called frequency divider. It takes an input, a clock input having a certain frequency, so this is the period t, and 1 over t is the frequency, but the frequency of the output is half of it, so the period is the double. You see from here. Now we are not happy, we want to do another thing. So we want to chain in series circuit like this one. So we understood that if we have a clock input, then the output of this one will have a frequency which is half of it, and therefore if we put another one, this would be half of this one, which means a fourth of the original one, and so on, an eighth of the original one. So if we go to our blackboard, we can try to represent this as a table of values that are changing in time. So what we are doing now is a sort of truth table for these sequential circuits. So it's like this. We have the clock value and then three outputs. Let's call them QC, QB, QA. So the time goes like this. So the clock can be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and so on forever. We know that the first flip-flop will divide this frequency by 2. So it's like this, 0, 0, 1, 1. We should do something like this in order to better visualize it. Okay, 0, 0, 1, 1, 0, 0, and so on. So this one will divide the frequency of the clock by 1/4. So it's 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, and so on. This one by 1/8. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, and so on. So now let me copy the clock column here. Zero, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Now if we read this table, we have those numbers: 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. So this number in decimal forms are 0, 1, 1, 0 is the number 2, 0, 0, 1, 1 is the number 3, 0, 1, 0, 0 is the number 4, 0, 1, 0, 1 is the number 5, and so on, until the moment in which we will have a 1, 1, 1, 1, and then this thing will, with the next impulse, turn back to 0, 0, 0, 0. So this thing is a counter that will count from 0 to 15 and back. Okay. Okay, so now by assembling this circuit, we found that we can produce a counter. So now we have another thing, which is the last ingredient we need to understand how a computer can compute something, which is called the arithmetic logic unit. So let's try to do this and then we will continue next time. So what you see here is some logic gates connected in this circuit, and for instance what you see here is a AND gate. So we said that the AND gate can compute multiplication between two bits A and B. Then we said that the OR gate can produce a calculated summation, but not exactly. In fact, if we want to be more exact, we have to modify the OR gate and create the so-called exclusive OR gate, which is this circuit we see below here. So this is one possible implementation of the so-called XOR exclusive OR gate. It's made with NAND gates only. And if we carefully study the behavior of this circuit, we will see that it will be representing this truth table. So let's read it like this. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals, it would be 2, that in binary code will be 1, 0. So we say that the result is 0, and we carry the 1 to the next digit. So this exclusive OR will represent the summation. So here we have a circuit where two inputs A and B are simultaneously presented to a circuit that will calculate A multiplied B, and to another one that will calculate A plus B. Then we have a third input, which is called OP, that stands for operand, or operation. So these two are the operands. While this one will be used in order to select the operation among those two operands. So let's go back quickly to the notes and let's analyze this circuit. We put an AND gate with two inputs. Now I draw them like this, and we call this input X and this input C control. So the truth table of a AND gate is like this. So the output is 1 only in this case. So if we consider here one input to be X, according to this truth table, if the control is activated, then we have X at the output, meaning that if we stick this to be equal to 1, for instance this is our control, so if we are at 1, if the other input which we call X is 0, then the output is 0. If it is 1, then the output is 1. So in this way, this AND gate operates as a switcher in the sense that it lets X passing from the input to the output, whatever it is. If it is a 0, we have a 0. If it is a 1, we have a 1, only if the input C is activated to 1, otherwise we have a 0. So this operation is called gating. Okay, so if we go back to the slides, Now we see that the result of this operation, that was a plus b, and here it was a multiplied b, is passed here and here by an AND gate which is controlled by the operation input. So if this input here is activated, then this gate will work in this gating modality, and then I will have a multiplied b here, and here I will have a 0. So there is this NOT gate, so here we have another AND gate working in this gating behavior, but the operation input is connected to this and to this one in a complementary way. So when we activate this, the other one is deactivated, so we have a 0, and vice versa. Then, because here we have an OR gate, in this situation, when here we have the multiplication, we know that the truth table of the operation is that if this multiplication can be either 0 or 1, if here we have a 0, the result is whatever was present in this input, so it's a multiplied b. So here we have that when we set the operation input equal to 1, the output is the result of a multiplied b. Similarly, if we set the operation input equal to 0, then the result will be the opposite path, so a plus b. So this thing is a very simple example of arithmetic logic unit. So we have a device that is able to compute, in this case, two different operations, a plus b or a multiplied b, according to another input that select which circuit will work in order to produce the result here at the output. So next time we will put all these things together in order to build the simplest possible model of a CPU.